I'm not going to even try to start the talk in Russian, because you already know that I don't speak. Just a short info about me, even if this is my, let's say, 5th C++ Russia or C++ Siberia. I'm one of the new things in this slide is that I'm now working at KDAB. And another new thing is that the book Functional Programming in C++ is now available in Korean and Polish, which is so weird. As usual, I start all of my talks with my favorite quote by Phil Wadler, the guy on the left. Make your code readable. Pretend the next person who looks at your code is a psychopath and they know where you live. This is the true words have never been spoken. So I really, really recommend you to watch Philip Wadler's talks, even if they are not about C++. So if you remember the previous C++ Russia, I had a talk called Move Only C++ Design Part 1. And I kind of promised that this is going to be a part 2. Obviously, as always, when you have part 1, the part 2 never happens. So, and the second problem in this case was that I got a keynote slot. So people who haven't seen the part 1 wouldn't have the option and not to come. They don't have any other talks in parallel. So you can just imagine this is like you have the first part of the Star Wars, and then you eagerly expect the second one, and then you get Solo. So Solo, it's not a bad film, but definitely not the continuation. Now, you can look at this. Solo was in the same universe as Star Wars. So today's talk is going to be in the same universe as the previous one, just independent. So we are going to, because I was told that keynotes should be a little bit broader and not overly, that I should not go into specifics too much. We are going to cover a whole story, and I'm hoping that at least for everyone that at least one part of my presentation is going to be useful. We are going to start with one of the simplest examples of inefficiency in our programs. So we have a couple of strings, and we are doing the concatenation of those strings. The first things that we learn after we graduated from basic C++ is that this can be slow because all of the operations are creating temporaries, and even with move semantics, where most of these pluses are going to end up as appends, you're going to have a lot of moves, because always the plus operator returns a value and not a string ref. So a smarter developer would implement something like that, like this. We can calculate the total size of the string that we need and then just call append. So no moves, not anything. We have pre-allocated the necessary memory, and we have just copied all the source strings into it. And how can we, let's say, generalize this? If we have a vector of strings, in order to calculate the total size, we can just use std accumulate. Now, you will notice that in my slides, I'll use the notation introduced by the ranges library. I'm not going to pass pairs of iterators to algorithms. I'm going to pass the collections directly. In this case, we have a collection of strings. We are putting them all through a transformation that gets the size of those strings, and then we just accumulate all the results. And obviously, after that, we have a for loop that will just do append. So in essence, what we have implemented is something that does transform and then accumulate. In, let's say, other universes, this is often called MapReduce, and is one of the most useful idioms in programming. Now, there is a small problem with .reserve. It's not as efficient as it can be. Any ideas why? So you're reserving enough space to store the resulting string. But every time you call append, what happens? First, a check. Do I need to relocate? And then the increment of the size of the container. So you're doing the work that you know it doesn't need to be done because you have pre-allocated enough memory. There is no reason for append to check each time whether the string needs to be reallocated. So an alternative would be to actually call resize. In this case, we are going to have a string that is not a capacity of something, but we are going to have a string that really has the desired size. So whatever we do with it, we never need to check whether the relocation needs to happen or anything else. Now, obviously, we cannot use .append anymore, but we can use something much, much better. So in the standard library, we have std_copy algorithm, and we have std_memcopy. The question is, what result do we get from std_copy? We pass to it a collection and an output iterator. And what we get in return, we get an output iterator that points to an element after the last character copied. In essence, it's going to return us the position where we should copy the second string. And after the second string is copied, then we are going to get an iterator to where the third string should be copied to. So we have a signature that says a collection, so one type, a string, and we have an argument of an output iterator, and we get a result, a new output iterator. There is the most powerful algorithm in the standard library that accepts a function of almost the exact same signature. And we already seen the algorithm, it's accumulate. So what we can do is just say accumulate. We want to pass all the strings. The initial accumulator is going to be the iterator pointing to the first character in the result. And whenever copy is called, the accumulator is just going to be incremented. And this works quite well. Obviously, some people who are, let's say, more functionally oriented might complain that we have side effects here, etc., but it works really, really well. So the first string that we want to append is going to start at the beginning. We are going to get the iterator to one place after it, and at that place we can copy the next and next and the next. The main reason why people don't really consider accumulate to be as powerful as it is that we often see it just as a tool to sum a list of numbers, concatenate a list of strings, etc. in an inefficient way. The power of std_accumulate, as we've seen in the copying example, comes from the fact that the accumulator or the initial value doesn't need to be of the same type as the values that we are traversing over. And we can implement, let's say, 80% of algorithms in the standard library just by using std_accumulate. We are going to see kind of how. Obviously, nobody is going to implement anything like I'll show in a few slides, because everybody will use for loops instead, and I would advise you to use for loops instead of what I'm going to show. But we are going to have, even if Sean is in the audience, I advise you to use for loops, and you'll see why. But the idea that we can do complex stuff with std_accumulate is going to help us in the second section of the talk. So what if we want to not only to return a joint string, but we also want to return iterators, so a list, a vector of iterators that points to exact locations where the original strings are found in the resulting. We can just make a more complex accumulator type. So in the previous version, our accumulator type was an iterator. If we need to calculate several things, we can just create a structure that contains all the things that we need to pass in through all the iterations of std_accumulate. So instead of having a single type, we're going to have a container of several values. So since we've said we want to have iterators to all the strings that we've copied, this means that apart from the output iterator that we already had, we need to add a vector of iterators to our accumulator. So when we've created the accumulator type, the next question is, okay, what's the initial value? Before we execute the algorithm, obviously the iterator is still the same. We are pointing to, the output iterator is the same. We are pointing to a 0th element of the resulting string. And since we haven't copied any of the strings yet, then we don't have any iterators pointing to already copied strings. So we are going to have the iterator to begin, and we are going to have an empty vector. And what should we do in the lambda that we are passing to std accumulate? We can just add the current destination iterator to the vector, and then call std copy, or in this case, range copy. So with each iteration, we are updating both of the values inside of the accumulator. One value is the vector of previously collected iterators, and the other value is, as it was before, the iterator to the next point where the next string should come. If you join everything into a single slide, after calling accumulate, we have a new value called ACC, and we can just access acc.dest will be iterated to the end of the original string, because that's the last value the accumulator is going to get. And we have all the intermediate points for all the iterators that we've calculated. So in the ACC points, we're going to get iterators where we have copied each of the original strings. Now, this could be quite useful if you want to create something like a resource library and you want to put everything in a huge block of data, but you still need pointers to where each of the elements in the resource are stored at. So we can pretend that we can return std pair of std string and a vector of string views from this function. Now, why am I saying we can pretend? Because this will probably lead in undefined behavior. Instead of returning a list of string views, we should probably return the indices of where the actual strings start, because this way we will probably end up with string views to an erased string when it relocates, when we return it from a function. So this was the first section, the power of accumulate. Any questions so far? Okay, so the comment was that the pointers point to one part of the memory and it reallocates, so it will end up in another. So we have resized the string. So the pointers until we return from the function are still valid. That's why I said that the problematic part is returning the string, because even with our resizing and everything else, it can be moved to some other place that might invalidate the string views. But for normal appending, the previous part, we have resized the string to be sufficiently large to store all the whole result. So during the appending, no relocation will happen. Yeah. So in essence, we had accumulate to calculate the size, and then the accumulate to do std copies. Okay. So the question is, why are there no overloads for R-value references for plus? They are, but they return std string, not std string ref. So that return value needs to be constructed, and the temporary will be moved into it. So when you have pluses on temporaries, you are going to get an append on the temporary and then move into the result. So move is O of 1, right? And doing nothing is of 0. Okay. Okay, so the comment is that I should have reserved in the ACC type as well. I agree. Okay, so one thing that I want to note is that string concatenation is kind of an example to drive the story about accumulate, not the point itself. But obviously, you're right. There are so many string copying functions and concatenation functions that are really, really fast. Okay, so now imagine that I'm not talking about string concatenation anymore, even if it's going to be about strings and concatenation. So just imagine the other way to abstract. Instead of having a collection of strings, we want to have a variadic template pack of strings. Now the question is accumulate. Does accumulate work on a variadic pack, template pack? Obviously not, but we need to think of something that behaves exactly like accumulate, but works at compile time for a template pack. And that thing has been mentioned a couple of times today. Those are fold expressions. So a fold expression is just accumulate with a really, really weird syntax. Or accumulate is a fold expression with a weird syntax, depending on what you like more. So what does a fold expression have? It has an initial value, which can be explicit or implicit. It has accumulation function, which in previous case was a lambda that we passed to std accumulate. And we have the collection of values that we are traversing through. What's more, if we don't write values, but say f of values, we no longer have just an accumulate. We have transform plus accumulate. So a fold expression should have probably been called MapReduce expression, because it allows both mapping or transformation and accumulation or reduction or folding, whatever term you like. So if you're going to rewrite the previous function not to work with vectors but with template packs, we can just say total size is going to be 0 plus etc. plus strings.size. So this is accumulate with an initial 0, then the operation is addition, and we are traversing over all the strings. And this kind of, apart from, let's say, different syntax, this is line by line equivalent to the previous example. What should we do in order to actually copy the stuff? We can, again, simulate the previous accumulate. We can say, in the initial example, the initial value for accumulation was the begin iterator, so it will stay the initial value. Then we have dot, 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 and we have a collection of strings. Now the problem here is that we need to use some operator. We can't use really default expressions with an arbitrary lambda. So we can't say dot begin, then lambda dot, dot, dot strings. So we will need to define some kind of operator. Usually operators like less than, or shift left are used. And it would look exactly like the lambda looked in the previous example. The only problem is that it's not inline, it's separated from our current function that we are implementing. Now the question is, are we able to somehow hide this and get the same syntax as accumulate? What we've said is that if we want to have a couple of values go through accumulate, we can just create a more complex data structure which contains all the values. In this case, if we want to create something more generic that looks like std accumulate, the thing that we need to pass through all the folding, so through all the folding operators, is not only a value, not only the accumulator, but we also need to pass the function, the custom function which will be a customization point in our code. So the structure for something like this would be an accumulator. We have a generic type. Init will be for the type of the accumulator or the initial value. And we are going to have a type named fun, which will contain inside the callable object for the operation for folding. And the constructor is quite trivial, and we can use ctad to instantiate the initial value. The operator less than will be quite trivial as well. We are just going to create a new version of the accumulator. The df doesn't change. df is the same for all the folding process. The only thing that changes is that we are going to call df for the previous value of accumulator, and we are going to forward the current value t to it. Std invoke obviously used in order to support all callables, not just function objects. Is this fine so far? Now, when we exit the fold expression, we really don't care about the f inside of this accumulator, so we can just create a cast operator from the accumulator object into the init type, which will give us the final value. So this can be used quite trivially. We can say accumulator t, initial value is 0, the folding operation is std plus, and we are going to traverse over all string sizes. Now, the cool thing about accumulate is that even if we call something MapReduce, the whole MapReduce can be just the reduce. It can be wrapped inside of accumulate, the whole process. So we don't really need ever to use struts.size. We can just create a lambda that accepts a previous accumulated size, the current string, and we can just return the previously accumulated size plus the string. Now we don't even need to write struts.size. We can just use it, move the transformation part into the accumulator function itself. And obviously the next step, because this still doesn't have the same syntax or similar syntax as std accumulate, is to wrap this inside of a generic function. Now the only difference is that the collection is not the first argument or the first two arguments, but we first have the initial value, then the function, and then all the strings that we want to operate on. So if we want to concatenate a pack of strings, we can use accumulate in order to get the total size by saying 0 is the initial, add size is the operation, and pass through all the strings. And in order to copy all the data, we can say just accumulate initial value for the iterator is result begin. The operation is exactly the same as it was in the previous one, and we can just forward all the strings as a collection. Again, not as a collection, but as a template pack. So the fold expressions are really, really powerful. The only downside is that you need to implement the operator that you are going to fold over. But if you create an abstraction like this, you don't even need to have a separate out-of-line definition of the folding function. You can just use a lambda and use this wrapper as is. Any questions for this part? Okay, cool. So let's move on a little bit more into templatey stuff. Sorry, what the heck? Okay, so imagine you live in object-oriented world. Obviously, most of C++ developers that are not present at this conference live still in the object-oriented world. And you're going to have an animal class, you're going to have a dog class or something like that. And obviously, the dog needs to inherit from the animal. Now, imagine you have a function that accepts a constref to a vector of animal pointers. And imagine you have a vector of dog pointers. Can you call the function with std vector of dogs? It's a compile error. Is it a sane assumption that you would be able to call this? If you have a collection of pointers to dogs, those dogs are animals. So it would be quite sane if you could just call this function on a collection of dogs. Now, this is something that is called, in theory, called covariant types. If we have a type A that inherits from a type B, then having a vector of type A's pointers should be usable as a vector of type B pointers. So we can try to do something about this. We can create a generic, let's say, function, although it says concept in the slide. The generic function or a concept is going to get to check whether a type from can be used as a type to. How can we do this? So all the collection classes in the C++ standard library, and Boost and Qt, etc., have a meta information about them called value type. So if we have a collection, we can extract the type of the value that can be stored in that collection. So for std string of ints, it will be an int. For std vector of animal pointers, it will be an animal pointer. So with regards to covariant types in C++, we can't really have a vector of values, because if we try to use a dog as an animal as a value, then we will get slicing. In object-oriented world, everything is a pointer. So these all need to be pointers. So we have just deduced that we want to convert dog pointer to a cat to an animal pointer. We need to remove the pointers. We can dereference and then remove constrefs. And this could theoretically even work with combination of different pointer types, like unique pointers and raw pointers, etc. Don't try this at home. I use this only with the same pointer types, not to incur any problems. In essence, you could always be able to convert a smart pointer to a raw pointer or something, but not vice versa. And we can just check whether from T is, if 2T is a base class of from T. So if you want to write a function that works on all vectors of all types that inherit from an animal, we can just say, okay, we want to write a generic function which is templated on a collection. And then we can just use concepts and say, okay, we require that this collection is covariant with std vector of animal pointer. Now, obviously, the syntax might be a little bit ugly. So we can even make it a little bit shorter. So now it looks like almost like an ordinary function. We have something that looks like a type called covariant of something, which is not really a type, it's a set of types that satisfy a requirement or a concept. And this now looks quite readable. We have different syntax. If you want to catch exactly std vector of animal, then we have one syntax, the classical syntax for it. If you want to extend the set of types, we can just transform it using this requirement and say covariant of all the std vector of animal pointers. Okay? No questions? Sorry? You'll need to get a microphone after, and then I'll hear you.
Why don't you just use doc type in here? You could make print animals, accept any type of any container of any types, which just implement the operations of the animal, and the compiler will just tell you that, oh, sorry, this is not animal because he can bark or something like this. And you have a special constraint here, which makes your code a little less generic. So why would you use this?
Okay. Since you had the microphone, I don't need to repeat the question. Like anything else, if you don't put constraints, you're going to get weird template errors, which is the first reason. And the second reason is that if you constrained this implementation, then you can provide print animals for other types, which are also generic. So constraints or concepts serve a really, really important purpose here. This is true. We are constraining ourselves to be less generic, but in this case, it's actually a good choice.
I have a question. Will this work if we pass a set, for example, of docs, of doc pointers? Not, yeah, but because I see that here it is covariant of vector, but actually, if we use your concept covariant, it will also accept set. Is it right?
Probably.
Yeah, and
it will break for sets.
Because it's kind of, in the declaration, it tells me it's kind of vector, but this concept actually is more like collection of something.
Okay, true. It's more a collection of something, and then you would get the error when you try to use the API of a vector that doesn't exist in a set.
Yeah, sure, but we want to use concepts, so...
But if you use concepts, then we can constrain this even further by using templates to say this needs to be a vector, comma, of something, comma, as.
Okay.
Yeah.
Thank you.
Cool question. So meta types, apart from being really important for things like these, are also ubiquitous when you're working with if-const-expr. If you want to check whether types behave as you wish and provide two different implementations. Or obviously with tag dispatch, if you have a bidirectional iterable collection, then you can just implement partition with the basic two-finger algorithm, go from one and the other side and flip whenever something is wrong. But there is a partitioning algorithm that works for only forward iterators. So if you want it to be overly generic, you would provide just one implementation for forward ones, which is completely awful in performance-wise compared with the two-finger one. So if-const-expr and tag dispatch can help you to still be generic, but specialize in different cases to optimize your code. So we have seen that meta types or meta information about the types is something that is really, really important. Do we all agree? Okay, unless you work in object-oriented Java style C++. So the next step. Usually when you work with a lot of template stuff, eventually you're going to start working with expression templates. And when you start working with expression templates, you're going to hate your life and hate your wife or somebody else. So instead, we should try to devise better ways to work with expression templates. Now, the example that I've chosen here is, again, string-based in its core. So the robes data structure is one of the data structures that is often used in text editors. Instead of saving a huge string as a sequence of bytes in one block of memory, you create a binary tree, and each of the leaves contain just a chunk of the original string. And then you can really efficiently implement mutations while still persisting the old versions of the string. If you just change a small chunk, just, let's say, a shared copy, shallow copy of the tree, and change the leaves that need to be changed. Now, if you want to research ropes, either Google them or ask Sean, because he mentioned that they were used in Photoshop at some point. Yeah. So you have an excellent source of information on this topic. We are not really going to implement any string operations here. We are going to pretend that all the expression templates that we ever write are actually ropes. Because usually, expression templates are the result of calling some operator, and operators in C++ are largely binary operators. So you're always going to get kind of a binary tree. And the leaves might be a little bit more complex. So the leaves, we will allow them to change the type to contain a lot of types inside and whatever else. So if you want to implement something like a core data structure for expression templates, it would look quite close to this. So a structure called node, we have the left type, the right type, so the left type is the left subtree and the right type is the right subtree. We can create, because for ropes it's always important to know exactly how many elements a tree has, because we want to have fast traversal afterwards. So whenever we create an instance of the node template, we're going to calculate the node count as a sum of all the nodes in the left tree and all the, not all the nodes, all the leaves in the left tree and all the leaves in the right subtree. After this, we can implement quite an efficient access by index. In essence, whenever somebody wants a node at some index I, we can just check whether that I is larger than the number of leaves in the left subtree. If it is, then we are going to search for it in the right subtree. Otherwise, we are going to search for it in the left subtree. And we have index access in O of ln, or OE in depth of the expression template tree. So now we have index-based access to our collection. How can we implement, for example, usually we want that expression template to end up as a flat list of items or a tuple. So we can quite trivially, if we are able to generate a list of compile time integers from 0 to the size of the tree, we can create a tuple trivially by saying make tuple. We want the node at a specified index and just expand the parameter pack. Now, in this case, the parameter pack is the list of indices. We usually don't have the list of indices as a pack. We need to generate them, and thankfully, the standard library allows us to do this with make index sequence meta function. So, make index sequence meta function is going to generate, let's say, a compile time list 0, 1, etc. to n-1, where n is the number of leaves. And this is an implementation how to flatten out a tree without any, well, I'm lying, but without any recursion explicitly stated in these two functions. Obviously, the recursion is in the index-based access. Now, the reason why this is useful is that when you evaluate big trees and you do it in a classical recursive way, you often obviously collect everything in a tuple in the left subtree, then the right subtree, and then you do the concatenation of two tuples, which induces a lot of copies or moves or whatever. In this case, each element is accessed only once, so it's only once, one time it's moved or copied to its final destination. If you don't need a tuple, just want to do some folding over it, again, it's quite trivial, just write a fold expression that accesses the items by ID. We already seen how to create an index sequence. Questions?
How efficient is this node add operation in terms of the number of nodes?
It's of size of the tree, depth of the tree.
So effectively, you have this flattening done in n log n, right?
Yeah.
Well, if it's a balanced tree.
Of course.
Mm-hmm.
Now, the main point here is that you usually need to do it only once, and you obviously you pay the price during the compile time, but during the runtime, you have the direct access to everything. And in the leaves themselves, we said that we can contain as many items as we want. So it's probably going to be an std tuple or something like std tuple. And then the node.that is just going to rely on std get. So for the leaves, we are reusing the get from the standard library, and for anything above that, we are using our internal implementation that checks should they go left or should they go right. Now, usually ropes are wide data structures. So in an optimal situation, the depth of the tree is going to be shallow, but that's not going to be the case in most expression template libraries, because still the leaves are going to be quite small and the expression tree can grow quite large. So all the things that we've already seen are essentially nothing new. They're normal template metaprogramming, just maybe a little bit weird, but they're normal. So what isn't normal? Let's move a little bit to more meta information about the types. Again, when you implement these things, you usually don't end up just with left, right, and a couple of usings inside. You need to tag all your nodes, which type of the node it is, so that afterwards you can write generic code that checks, is this nested type definition present or not? And if it's present, is it a binary node tag? Is it some kind of other node tag? So in essence, if you've been at this morning's keynote with the sources and sinks, etc., you will probably want to know which node is a source, which node is a transformation node, and which node is a sink. And you can have completely different types for subtypes of all of these. So you will probably create a meta information like this. And obviously, since left and right subtrees are really important, you're also going to get using left T and using right T. Then, when you write a generic function that needs to check and use these, you can just say if const expr, then use the detection idiom that is going to be a part of the standard quite soon. std is detected exact. So you're checking, does your type have a node type tag? If it does, is it binary node tag? If it is, then do something with left T and right T. Does anybody see problems with this approach? So the problem is what usually happens when you don't really have properly designed types. Just imagine that somebody forgets to declare using left T and right T. This is something that often happens in normal data structures when you implement normal runtime stuff, not template metaprogramming code. If you forget any of these, you'll get a huge, huge, huge error. We should instead design our types so that they don't allow us to make mistakes, both at runtime and compile time. Instead, we can just create, instead of a normal structure for the tag, we can create a generic type for the tag. So we can make it a template on left and right, and when we are going to tag our class, we are going to have to write binary node tag and explicitly state both left and right items. We cannot forget it anyhow. The problem is that I'll need to speed up. My yellow light has just popped up. So we cannot use the isDetected anymore, because isDetected exact checks whether the type is exactly something. And we just want to check the first part, not the left and right parameters. So instead of that, let's see how isDetected exact is implemented. It uses the detection idiom to return a type of a certain tag and checks whether it is the same as what we expected. Instead of that, we need a function that can tell us whether a certain type is an instantiation of a specific template. So, for example, we want to have a way to check whether stud vector of int is an instantiation of stud vector. We can modify the definition of isDetected a little bit, and we can say, okay, isInstance of, we are going to have the name of the template captured as the template argument, and still the type is going to remain the same. By default, no types are the instances of this template thing on the top of the slide. But if the C++ language is able to do pattern matching and match the type that somebody gave us against template with any kind of arguments, then we are going to return true. So C++ has much more features during template metaprogramming time than during compilation time, during runtime. Pattern matching has been a feature of C++ since a long, long time ago, but not the C++ that most people want to write. And then we can just wrap this inside of a normal function, again, normal function, which is really weird to talk. When I say normal function and talking about template metaprogramming, it's obviously a normal meta function. The standard library provides us with _v of all the template stuff in it, which returns an actual value. So we can use the isInstance of v to implement a replacement for isDetected exact. We can implement isDetected instance of. Again, accepts which template we are trying to match against, which type, etc., and it will do exactly like the previous one, just, let's say, a little bit more generic. So we have solved one problem. Now we removed the possibility that we had to make errors. The problem with this approach is that the tags are fixed. All the tags are specifically defined using this, using this, using this. Whenever we want to move stuff and say, okay, we don't want to define it just right now, we can do a little awful trick and say, okay, whatever this becomes, I want to accept it. And in the terms of template coding, whatever is usually spelled tuple. So instead of using a specific thing, we can just create a big meta type and say, using meta t will be a list of tags that this current type contains. Just as you would normally do with std vector or anything similar. So we can have the left type, the right type, and some metadata that somebody gave us from the context. And we are adding new metadata to it. So we are adding binary node tag, this one, and we have all the previous base metadata inherited. So how can we check whether a type is tagged with something? We can just pass through all the types in the meta t2 tuple and say isInstance of. If we haven't found a tag, then obviously it will return false. How can we find the specific tag? So this is just a check whether the tag exists, but we often need to access the specific values inside of a tag, like left and right. We can do a fold or accumulate and just implement a filtering algorithm on top of using folds. If something satisfies the predicate, add it to the tuple. If it doesn't satisfy the predicate, ignore it. After we get this, we have extracted all the tags. From the list of tags, we have extracted the tags of the same type. Because this is a list, it's not a hash map or anything like that. We can have multiple instances of the same tag. So we have the equivalent of isDetectData-V. We have the equivalent of detected.t with a slight addition or omission if you don't like the fact that we can have several values of the same tag. So if we want to, we can just create an enriched node which inherits all the tags from the previous node that it's going to enrich. So we can even simulate normal object inheritance. We inherit all the tags and add our own. Okay? And obviously we can redefine a tag. If you're just interested in a single result, we can always, after filtering, access just the first found result. So it will be the last one defined, so it will be the last one defined for our class, not all the inherited tags of the same type. So now the question is this something that I just wanted to show because it's cool and tedious to write and etc.? That is the main reason as usual, but obviously all of these things have some use. Imagine you're writing a library that looks like ranges as far as the syntax is concerned, but you want to support, let's say, a little bit more operations than ranges v3 do. So you have a collection of x's, you are going to filter, you're going to sort, transform, and take 5. First, if you're going to look at the tags that our types are going to have, initially, just think of these as dummy nodes. No algorithm is behind them, they're just dummy nodes that specify what will be there at some point in the future. So the sort does nothing, transform does nothing, take does nothing, they're just dummy empty nodes. The only thing that they need to store, for x's, we'll need the meta information value type because it's a collection. For the filter, we will need the information about the predicate. For sorting, the comparison function. For transformations, transform function that we're going to use for transforming. And for take, initially we just need the limit. Now, the question is, can we deduce after the sorting, which will be the type of the value type? By itself, sort, again, is a dummy node. It doesn't know what's on the left-hand side. It doesn't know what's on the right-hand side. It cannot know which value it's going to accept, which value, type of value, and which type of values it's going to emit. So we are going to start with x's, use the value type from there, and pass it on through the whole pipeline. So after the first pipe, we can enrich the filter node and say, okay, you have stored the predicate so far. Now you also have the compile time meta tag that says you're going to emit strings. Because filter never changes the type of the values it receives, it just ignores some of them. So it will always be, if we get a collection of strings, after filtering, we are also going to have a collection of strings. After we sort, does anything changes? No. If we have a collection of strings, we sort them, we are going to get a new collection of strings. What happens with transform? Transform can change the type. So while we are piping, again, for this, we are going to get the information from sort. Which values sort returns? Okay, it returns strings. And we, for example, in this transformation, we have a function that converts strings to integers, parses them, or extracts the size or something else. Then transform is going to say, okay, my return type is not a string, it's an integer. And when we go to the take, again, the previous node will send the type to take. Take will say, okay, I never change types, I just clip the collection to a specified number of elements. So we don't need to do anything, we are going to deduce that this is an int. Now the question is, in the ranges library, you cannot really pipe sort as it's a normal view. And that's a decision that I never liked, but it was from what I know, decided by the standards committee that views can never own data. But something like this could be quite useful. The problem with writing code like this is that it can be quite inefficient. We want the top 5 elements, but we are sorting the whole collection, which is obviously useless, right? You don't want to sort billions of items n log n when you can just pass in O of n and collect all the 5 elements that you need. So we have just passed through the collection from left side to right side. Now we can do it in opposite direction. So while we are processing our nodes, take nodes that it needs just to partially evaluate elements of the previous collections. It just needs the first 5 and lazily ignore evaluating all the rest. So we can just write in the opposite direction and say, okay, so let's communicate this to our previous transformation, which is transform. Transform doesn't care. Transform emits as many elements as it receives, so it can just pass on that it still needs just partially to evaluate something. Again, partially, it can be a specified number of elements because we said tags can have metadata inside of them. Sort, on the other hand, even if it's going to emit just the top 5, it needs data to be evaluated. It needs to evaluate the whole input data. So it's not going to emit that it's a partial to its predecessor. The predecessors are going to remain the same. So we have just gotten std string, a vector of strings. We know that filter needs to filter all of them because it's not partial. Then sort knows that, okay, I can be a lazy sort and just sort a few elements that are requested from me. I don't need to sort the whole collection. And transform and take are also partially evaluated. And when we have finished processing the metatypes, this is still just talking about changing the types, never touching the values inside. When we evaluate, we can just move all the inner data from all the original temporary dummy nodes into our final enriched node structure. So, and this is where this kind of connects to my previous talk. So this is unofficially part 2, because this is really useful to do with linear types, with move-only types, because then you would get an error if anybody tries to copy something. So if you make a mistake during the implementation and accidentally copy values, if you develop this with linear or move-only types in mind, then you'll skip making those errors. So we have kind of implemented a dynamic property system that works at compile time. With inheritance, with searching, with checking, with removing. Well, we haven't implemented removing, but that could be done quite easily using the filter function that we already seen a little bit before. And this is so cool, the last minute. This is the end.